So as you see in my title here, I'm going to talk about two rather classical core topics of discrete geometry, unit sphere packings, and contact graphs. And as we know, unit sphere packings or packings are in general arrangements of finite or infinitely many, in this case, spheres without having overlaps. So no two unit spheres in the packing can share an interior point in common. Contact graphs are natural combinatorial objects assigned to packings. Vertices correspond to the packing elements, and edges correspond to touching packing elements. So if we have two vertices, then there is an edge between the two vertices, if and only if the corresponding packing elements, in this case spheres, touch each other. So besides these two classical concepts, I'm going to target something new, and that I put in green here. I'm going to talk about separable packings and their contact graphs. So somehow I felt I should do a little tour on contact graphs for unit sphere packings at the beginning, just to make the topic, the results more reasonable looking. So this part here reviews contact graphs of unit sphere packings. Of course, this is a topic that has been investigated in detail, so I'm not going to do a complete review, only few results I will review here. This book here is a resource, is in particular chapter 4, that could be used for further info. So let's start to review this. The historically correct sort of first topic is kissing numbers, because when we look at vertices of contact graphs, then, and we are interested in the highest degree of a vertex, then we end up with this beautiful geometric question, which is about the following. We take say a unit ball in Euclidean space. This talk is going to be very much Euclidean. So I take a unit ball in Euclidean D space, and the question is, what's the maximum number of non-overlapping unit balls that can touch a unit ball? Here on the left, you see the two-dimensional trivial case. 6 is this largest number. But if we increase the dimension, the problem changes the character in the sense that it's becoming more complex. In 3 space, you see here a red unit ball touched by 12 blue unit balls, and the vertices of the unit balls are positioned in the vertex set of an icosahedron. And the interesting fact about this diagram is that no two blue unit balls touch each other, so they can be moved around locally, maintaining the property that the arrangement of 12 unit balls is still a packing, and each member touches the red one. So which shows that in 3 dimensions, the matter is more delicate. Here's the complete list of exact values of kissing numbers of unit balls in D space. K of D is the kissing number, largest number of non-overlapping unit balls that can touch a unit ball. In dimension 3 is a classical result due to Schutt and van der Waden from 1953. This number is 12. In dimension 8 and 24, you see the exact values listed here, which has been proved by Odlyzko and Sloan, and also Levenstein proved this independently from them in 1979. The latest exact value was discovered by Oleg Musin, and that's in dimension 4, which his theorem states that the kissing number of 4-dimensional balls is 24. That's the complete list of exact values. So any progress on this is, of course, very interesting, and estimates are known for other dimensional cases. Here's an article, a recent one, on improving kissing number estimates using semi-definite programming. And I extracted a chart from this article just to illustrate that indeed a lot of effort has been made to gain further understanding of kissing numbers in small dimensions. In this case, up to dimension 23. You see the improvements. Improvements start in dimension 9. They are underlined here in the chart. So, you know, this is a laborious area and requires a lot of efforts, and it looks so that progress is coming along. If we really want to get a quick sort of understanding what's going on in very high dimensions, here's a recent publication which actually proved this beautiful result, an exponential lower bound for the kissing number. And here the dimension is not restricted, in fact, goes to infinity. And it is worth comparing this lower bound to the so-called obvious, trivial, still very elegant lower bound, which numerically looks like this value here, inequality number 1 I'm referring to. And that's a concept which is worth mentioning because it is elegantly simple. So if one can imagine a unit ball surrounded by unit balls, non-overlapping unit balls, such that their number is large as possible, and do the following, that project each unit ball touching the central one onto the surface of the central one, then in this way one gets a system of non-overlapping spherical caps on the central unit sphere, each having angular radius pi/6. And because they are non-overlapping, forming a packing, and because our assumption is that the configuration is a kind of maximal kissing configuration, these spherical caps form a so-called saturated packing on the central unit sphere, meaning that we cannot add any additional one to it without destroying the packing property. In other words, that means that if we enlarge each spherical cap having angular radius pi/3, enlarge each radius, double each radius, then we must get a covering of the unit sphere. In other words, the total surface volume of our enlarged spherical caps must be at least as large as the surface area of the unit sphere. And that results into this lower bound here, what you see on the right of the inequality 1. Now, when we compare that to theorem 1, we see the nice improvement. It's a linear improvement factored. There is an extra d here. We have square root of d in the lower bound of formula inequality 1. And now we have an extra d showing up in theorem 1. So this is a real breakthrough. This classical inequality number 1 has been known more than 50 years, and now we have an improvement. There is a counterpart to it, and that's an older result, not a recent one, and that goes back to Beretzky and Levenstein. It proves an exponential upper bound. And if we compare this upper bound to the lower bound that we have discussed on the previous slide, we see that there is an exponential gap. Here, the base of the exponential part is roughly 1.15, and in Beretzky-Levenstein upper bound, the base, similar base is 1.32, I believe. So there is a exponential gap between these two bounds. On the other hand, I put down here Rankine because Rankine, you know, there is an elegant upper bound on the kissing number of a d-dimensional unit ball, very similar to the one that we discussed for the lower bound. And that has been improved by Rankine using Blichfeld's method, which he extended to spherical spaces. So that's the Rankine bound here. And of course, Kabatsiansky-Levenstein beats that, as you see here. And that's roughly what one can say about kissing numbers in a brief review. Now, since we want to talk about contact graphs of unit sphere packings, we are led to this concept of contact numbers. So when we have a unit sphere packing in d-dimensional space, Euclidean space, and we look at the contact graph of that packing, we might want to understand the behavior of edges in this graph. And the question is, what is the maximum number of the edges that we can have for a contact graph of, say, n unit balls in Euclidean D space? The diagram here shows a very simple contact graph of the kissing configuration of the unit disk in the middle. And the contact graph is a nice graph consisting of you know, the faces are regular triangles here, 6 of them. And as we increase this number of the number of unit disks, the problem becomes harder. And so it was quite nice to learn that Harbord in '74 actually came up with an exact formula that tells the maximum number of edges of a contact graph of a packing of n unit disks in the plane. And this formula is lower integer part of 3n minus square root of 12 times n minus 3. So 12 times n minus 3 sits under the square root sign here. It was natural to ask the immediate question, can we say a bit more about this situation? What happens if we look at unit disk packings of n unit disk with maximum contact numbers? Can we characterize these extremal configurations? And the answer is yes. And this theory of Heitman and Redin states that if we take an extremal configuration, if we take n unit disk in the plane such that the contact graph has maximum number of edges, then the centers of the unit disk must sit in a triangular lattice. One can phrase this in this elegant way, as you see here in this page of the article, talking about minimizing the energy. The sticky potential is introduced here in such a way that our task is indeed maximize the number of touching pairs in the packing. So it was a happy ending story here in the plane, a complete understanding of this contact number problem, which naturally led the question in higher dimensions, led us to the question in higher dimensions. And in this article, there is a general upper bound on the number of touching pairs of packing elements. Well, the setting is a bit more general than in the previous slides. I take a convex body in Euclidean D space, and I look at n translates of non-overlapping translates of that convex body K. And the question is, can we say anything? Can we come up with an upper bound for the number of touching pairs? in such a packing? And the answer is, you see here in this formula, and there are two quantities which play a role here. We are packing n translates, and the leading coefficient here is something that people have studied independently from this question. It is called the Hedwiger number. H of K0 is the Hedwiger number of K0. Here, K0, K sub O, refers to the Minkowski symmetrization of K. K need not to be centrally symmetric, but this symmetrization procedure, where we take K and negative K and the vector sum of these two and normalize it with factor 1/2, is a centrally symmetric convex body. And moreover, this symmetrization preserves the packing property. So if we have n translates of K forming a packing and we symmetrize each K with respect to the same point, we get a packing of the centrally symmetric convex bodies. And the other quantity that enters into this formula, upper bound, is delta of K0, which is the largest possible density of packings of translates of this origin symmetric convex body. This largest density one can think of simply as the fraction of space occupied by translates of K0 forming a packing in the space. So the formula has these two quantities showing up there, and there is a linear part here and a kind of an isoparametric part where n is raised to d minus 1 over d, and the coefficient is a bit complicated, but this IQ here is an isoparametric quotient. So if K0 happens to be a ball, then this is not there. This is just 1. And that means that this formula we can apply to the contact number problem for packings of unit balls. And if we do so, we get the following corollary. And this is briefly written on this slide. So as you see here, in higher dimensions, the formula that I showed on the previous page is translated into this formula. Tau d is the analog quantity of the Hedwiger number. This is the Kissing number, d-dimensional Kissing number of the unit ball. And delta d refers to the highest density of unit ball packings in D space. So this is what we know then in very high dimensions about upper bounding the contact numbers of packings of unit balls, of n unit balls. If we lower the dimension to 3, in dimension 3, the above formula is translated into this one. Well, actually, translation here means that I'm using his result, that the highest density of unit ball packings in 3 space is pi over square root of 18. The asymptotic formula that you see in the middle is obtained from the formula on the top using the Kapatiansky-Leverstein's bound for the Kissing number that we already briefly discussed, and there is an analog result of them for the highest density, upper bounding the highest density of unit ball packings in D space. So I just want to focus on the 3-dimensional case for a few more minutes and see whether we can do better than this here, this result here. Can we improve this upper bound on the contact numbers of unit ball packings? And the answer is yes. In dimension 3, one can do this. And these papers are references here. And the actual improvement is I try to summarize on this page. So the improvement is right on the top corner. So this theorem says that if we pack n unit balls in 3 space, and we want to upper bound the number of touching pairs in this packing, then this bound works. So the coefficient is larger than on the previous slide here. It was 0.152 in front of n raised 2/3. Now it is larger. It is 0.926. Well, one of course has to compare to this what we can do, and this is briefly stated in the second part of the theorem. They are relatively simple arrangements of unit balls that exhibit contact numbers of this order. You see here this formula, 6n minus 3.665 times n raised to 2/3. Geometrically, what is happening is the following. For specific values of n, namely for these values of n, one can generate a kind of octahedral arrangement of unit ball packings. This is obtained from the face-centered cubic lattice packing of unit balls, where the Delaunay cells are regular simplices and regular octahedra. And if one put together tetrahedra and octahedra in this fashion, as it is indicated in this diagram, we can generate huge octahedra. And this can be done for these values, integer values, generated by k. So k in my diagram is actually 4. There are 4 center points along one edge of my regular octahedron. Each dot here, black dot here, is the center of a unit ball. So the edge length of my octahedron is k times 2. Nevertheless, if we do this construction, we get the feeling that these are nice arrangements, and I believe that these are exhibiting largest possible contact numbers for these values of k. For the other values of n, it has been observed by other people that this restriction here is not necessary for the lower bound, and it works for, or this lower bound here works for all n. And so the question arises: is there a limit here? Is there, and what is that limit? I really don't know, but it has been, this problem has been studied in a very nice paper enumerating rigid sphere packings, and the result that I can quote here is this chart at the bottom. In the paper, the maximum number of the contact number of packings of any unit balls is labeled by capital M of n. So this middle row here represents those maximum numbers that was found with the classification of rigid sphere packings for the specific values that you see here, starting from 5 up to 19. And indeed, for 6 and 19, which corresponds for k equals 2 and k equals 3, the maximum contact number that was found is 12 and 60, which corresponds to this octahedral arrangement that we discussed on the previous page. And when you look at this chart, the interesting thing that is worth observing is that the lower bound that I stated on the previous slide does a reasonable good job here. It is not far at all from those largest contact numbers found in this paper. The difference is typically 1, except in case of 12, where the lower bound is off by 2. So this is it, what I just wanted to say about contact numbers of unit sphere packings in 3 space. It is clear that we still have challenging questions left here, and it would be nice to progress it further. I want to switch over to a family of packings which are going to play the main role here in my talk. And these are, as I mentioned on the first slide, these are separable sphere packings. And the story starts with totally separable unit sphere packings. This concept is illustrated here on my slide. So if we have a packing of unit balls in Euclidean D space, we call it totally separable if the following happens, if the following property holds. No matter we choose 2 unit balls, say I choose this green unit ball here and then the yellow one, there must exist a hyperplane separating them such that that hyperplane, in this case, this horizontal line, is disjoint from the interiors of the packing elements. This line that separates my 2 chosen packing elements must be disjoint from the interior of each and every packing element. If that holds for any 2 pairs of unit balls, we call the packing totally separable. Putting it somewhat differently, one way to generate a totally separable packing of unit balls is that you start with an hyperplane arrangement, and then you put unit balls into the cells, chambers, where you have sufficient space for having the unit ball. And in this way, we get a unit ball packing. Now, this concept was introduced by the 2 Feierstotts in the 70s, in the early 70s, actually in 73, in this paper. And their question was more a volumetric one. They were interested in the highest density of totally separable packings of unit disks. And if, in fact, they could do a bit more in the plane, they could take any centrally symmetric convex domain, such as this ellipse-looking oval, and they generated a totally separable packing using translates of that oval. As you see in this diagram here, this is a totally separable packing of translates on the oval. And their theorem states that the highest density we obtain if we take the smallest area quadrilateral, circumscribed, or centrally symmetric domain. That is always a parallelogram. And then if we extend the size of the parallelogram and extend the parallelogram to a tiling of side-by-side tiling of the plane, then the inscribed ovals form the densest packing, totally separable packing. This is a very nice 2-dimensional result. Now, of course, we are interested in contour graphs of totally separable packings, and we want to understand, find the largest contact number of n translates of totally separable packings. Their paper generated a lot of interest in totally separable packings, and that's a topic, especially the highest density, finding the highest density, that is interesting on its own. I'm not going to towards that direction. Instead, as I said, I'm interested in contact graphs of totally separable packings. And it is it was surprising to me that actually, independently from Feierstadt's paper, people had looked at this concept of totally separable packing somewhat in a more special way. Alonso and Cerf paper that I'm quoting here is quite lengthy paper and deals with the following question. We take the integer lattice and we now generate packings of n unit disk and then unit balls in 3 space centered at some points of the integer lattice. And then we want to maximize the number of touching pairs. So what, again, what we do, we take the integer lattice, we generate a totally separable packing, but in this very special way, the center points of the unit diameter balls are integer points, and we take n of them. They form a totally separable packing, and our task is to maximize the number of touching pairs. Now, here in the diagram on the left, you see 13 cells of the square tiling highlighted. Each cell holds a unit diameter disk. They are not really drawn here. And when we have two unit squares sharing a side in common, that means the inscribed unit diameter disks touch each other. And so what we have here is a rather geometric problem. Besides having, it has a combinatorial character, it is actually an isoparametric problem. Because what we want, for given n, we want to find n unit squares in our square tiling such that the parameter of their union is minimal. Why is that? Because our task is to maximize the number of touching pairs of unit disks. In other words, we want to maximize the number of unit squares which share a line segment in common. And while we are doing it, we actually minimizing the parameter of the union of the unit disks. And similarly, in 3 space, the isoparametric problem that we are having here is how to position n unit cube and unit cubes in 3 space, chosen from the cube tiling, the unit cube tiling of 3 space, such that the union of the n chosen unit cube has a minimal surface area. And the answer is this diagram here tells us how to do this. We have to put the n unit cubes as close to each other as possible, forming a quasi-cube. Arithmetically or algebraically, what happens is there is an exact formula in the 2-dimensional case for the maximum contact number of these totally separable packings with center points chosen from the integer lattice, lower integer part 2n minus 2 times square root of n. And in 3 space, there is no exact formula. One would not expect an exact formula, only an approximate one, as you see here. Now, the question was, what can we do when we get rid of this underlying lattice structure and we allow to have a totally separate unit sphere packings in general? Can we come up with an upper bound for the contact numbers? And the answer is summarized here. First, I again return to this lattice setup because the result that we have just discussed on the previous slide was 3-dimensional. Now I increase the dimension and we take a d-dimensional cubic lattice. And in other words, we generate special totally separable packings of unit diameter balls having integer coordinates. And question is how large this contact number can be. And the answer, the formula is right here. And the proof is not that lengthy at all, unlike the approach, which is rather algorithmic in these in the 2- and 3-dimensional case. This is based on the Brun-Minkowski inequality, and that gives this upper bound, which is sharp in dimension 2, and in dimension d, it is sharp for all integer n, which is a power of k, which is of this form, k to the d. And it is not that bad for other values of n either. Nevertheless, for other values of n, this is not an exact formula. This is just an upper bound. If we move to totally separable packings of unit balls in D space, the upper bound that we could prove, you see here, still of the same character, d times n is the leading term, and there is an isoparametric term subtracted with this factor. In 3 dimensions, the best upper bound you see here in Theorem 3. And of course, I cannot resist to put forward this conjecture that maybe this is true in general, that this lattice contact number is the same, maximum contact number is the same as the maximum contact number for totally separable packings. I could speculate on this further, but I'm not going to do this. So let's finally discuss a locally separable unit sphere packings, which is the concept which is new here. In this diagram, I'm trying to describe what is this notion being locally separable. It is a relaxing version of totally separable. When you look at this packing here of congruent balls, say unit disk, and you take any unit disk, so for instance, this unit disk, which is touched by 3 others, then this unit disk and its neighbors, touching neighbors, form actually a totally separable packing. Although the entire packing is not totally separable, it is locally totally separable. It means that each unit ball, together with its neighbors, touching neighbors, must form a totally separable packing. So what we want now, we want to look at locally separable packings. This is a much larger family than the family of totally separable packings. And we want to get some understanding of the behavior of the contact graphs of locally separable packings of unit balls. And this paper does it, and one can find it on the archive. So let me just state the 2 results that I will discuss in some details on the next slides. Both are motivated by this conjecture. I believe that even though we relax the property of being totally separable, these 2 packings, the family of totally separable packings and the family of locally separable packings, must behave the same way with respect to the contact number problem. So the largest contact numbers are equal to each other. I can prove this only in the plane, and I will state that result. So it is really wide open, this conjecture here. So first result is towards this conjecture, is an upper bound on the locally separable packings. In fact, what I could do here, I could improve the earlier upper bounds, contact number upper bounds on for totally separable packings, for locally separable packings. So this upper bound that you see here is better than the earlier upper bound on the contact numbers of totally separable packings. So if I go back to this slide here, for any packing of any unit balls in this space forming a totally separable packing, the contact number of that packing is at most this large. Here the coefficient of the isoparametric term is 1 over 2 times d raised to d minus 1 over 2, which has been replaced by a larger coefficient in this theorem. There is a new quantity entering here, which is not really new, and I'm using the notation delta sub d hat. This is not the largest density of unit ball packings in D space. It is a variant of it. What I'm doing here, I'm taking a unit ball packing in D space, BD of C sub I. 1 refers to be the packing elements. So this is a unit ball centered at the point Ci, and they can be finite or infinite. They must form a packing. And when we have such a packing, each unit ball has a Voronoi cell assigned to it, and we truncate its Voronoi cell by a ball concentric to the unit ball having radius square root of d. And I'm looking at the density of each unit ball in its truncated Voronoi cell and maximize it for all packings of unit balls. This is this quantity delta, the sub d hat. And this quantity enters here into this estimate here, upper estimate for the contact number. And I will very briefly say why this quantity is interesting. And then we take a diagonal look of the proof of this theorem. So this quantity that I'm using for my upper bound of the contact number of an arbitrary locally separable unit ball packing D space is not new. The notation that I'm using is delta sub d hat, and this has been looked at before. Most concrete, well, the origin is Rogers. Rogers upper bound for unit ball packings is a very geometric upper bound, which is, one can briefly say you take a d-dimensional regular simplex of edge length 2, and you draw unit balls centered around each vertex of the simplex, and you take the fraction of the simplex covered by the unit balls to, and that volumetric fraction is an upper bound on the density of unit balls in D space, and this is usually labeled by sigma sub d. This is Rogers' upper bound. And it turns out that actually Rogers proved more. What he proved was that he proved that the density of a unit ball in its truncated Voronoi cell is upper bounded by sigma sub d, where the truncation radius is not square root of d, which I have been using in my theorem. It is much smaller. It is square root of 2d over d plus 1. So that means that one can actually conclude that this quantity that we introduced on the previous slide, delta sub d hat, is upper bounded actually by Rogers quantity sigma sub d. So this upper bound that I proved stated on the previous slide for the contact number of an arbitrary locally separable unit ball packing, it can be further upper bound it using sigma sub d. This is what I'm doing. And if you use the asymptotic formula for sigma sub d, then we get a sort of understanding, a better understanding of the order of magnitude of the estimate that we have here. And the other theorem that I have here for locally separable unit ball packings for their contact numbers is more pleasing. It is a full complete understanding of the maximum contact number problem for locally separable unit disk packings. First of all, there is this upper bound on the contact number. And if we can refresh our knowledge of contact numbers that we briefly reviewed before, we discovered that, yeah, even though we relaxed the condition significantly compared to the very first condition when we have chosen looked at unit disk packings of n unit disk with center points chosen from a special lattice, we cannot really increase the maximum contact number. So locally separable unit disk packings behaves the same way as totally separable unit disk packings, which behave the same way as unit disk packings with centers chosen from a lattice in the plane. And the maximum contact number is obtained with this nice formula. In fact, one can do more. There is a crystallization result, which is an analog of Charles Radin's crystallization result, Heitman-Radin's crystallization result. Namely, we can characterize the extremal configurations completely. So if now we take a locally separable unit disk packing in the plane with maximum possible contact number for a given n, and we imagine that the contact graph is actually embedded in the plane such that the center point, the vertices are center points of our unit diameter disk, and edges of our contact graphs are line segment of unit lengths connecting the center points. Then the extremal contact graphs are of the following type. Either we have the contact graph of our extremal locally separate disk packing identical to the contact graph of the packing of 7 unit disks, here illustrated on the right, or the contact graph is two connected, vertex two connected, whose internal faces form an edge-to-edge connecting family of unit squares. Here you see an illustration of that. Here I have drawn the maximum contact graph of 11 unit disks, forming actually not only a locally separate, but total separate packing, such that the internal faces of the contact graphs are unit squares and they form a polyomino. This edge-to-edge connected system of unit squares is called a polyomino. This is another scenario, and there are two more possibilities here. Or the extremal contact graph is still two connected, whose internal faces are unit squares, forming a polyomino of an isometric copy of the integer lattice, with the exception of one internal face, which is a pentagon. This diagram here is an illustration of that case. So it can happen that we have a pentagon attached to or polyomino in the fashion as the diagram indicates, which happens in case of 13 unit diameter disk. Or, and that's the final option, here, the fourth scenario, is that there is a degree 1 vertex on the boundary of the external face of the contact graph. This unit disk, its center represents the degree 1 vertex. such that deleting that vertex together with the edge adjacent to it yields a two connected graph whose internal faces form a polyomino of an isometric copy of the integer lattice. So that's the complete answer to the crystallization question in the plane. Now what I really would like to do, I should probably say a few words about the proof of the upper bound theorem for contact numbers of locally separable packings. But I'm running out of time, so what I just want to emphasize here, this proof that is behind this theorem is of volumetric nature, and the driving force of the proof is comes from the following source. Here, the diagram illustrates what one should say very briefly about the proof. So the yellow disk here illustrates the bores that we pack. So we have n unit bores in D space forming a locally separable packing, and we want to get an upper bound on the maximum on the contact number of this packing. What we do, we introduce gauge spheres here. Spheres of, these are concentric to our unit bores, and their radii are equal to square root of D. And then in this way, we generate overlapping bores, larger bores, and they generate, and we look at the reunion. And the proof is an isometric property, is based on an isoparametric property of the union of these larger bores. The proof gives a lower bound on the surface area of these bores, as well as an upper bound. And these lower and upper bounds then lead us to an upper bound on the contact number, because the upper bound on the surface area is an expression into which the contact number enters. Another source why this proof is actually working, another input which makes the proof possible is Beretzky's upper bound theorem. So that theorem is an analog of is about upper bounding the density of spherical caps forming a packing in spherical space. So although our contact number theorem is a Euclidean one, since the proof is based on understanding the behavior of the surface area of this highly non-convex union of concentric gauge spheres, the actual underlying technology is an analytic technology in spherical space. And that spherical space luckily has a technology based on Beretzky's upper bound theorem, which is an upper bound theorem analog to Rogers, upper bounding the density of upper bounding the density of packings on congruent spherical caps in spherical D space. So these are the, roughly speaking, this is the description of the proof. So I'm skipping that part completely, and although there is a lot to say about the two-dimensional case as well, I will not do that. So I stop here. Thank you.
Thank you. Thank you very much. Are there any questions?
Can I ask a question? Hi, Karoly, this is Oleg. I don't know what happened with my video. Can you say something about the following extension of your problem? Suppose you have a not any and the periodic packing, right? For instance, we have a flat square, right, in the plane. And in this case, can you say, even in two-dimensional case, but it is interesting how to find the maximum contact numbers. I mean, you can ask the same question for a given torus, flat torus, right?
Yeah.
It's the same question for the past one, past two, and past. Yeah, and you have a three different questions. Can you say something about this upper bound for contact numbers? Even in two-dimensional, clear for me.
Yeah, it's a very, very good question. Thank you, Oleg, for asking that question. You know, this is an ideal sort of extension of or a research direction. Mm-hmm. Unfortunately, however, you know, I am still at an earlier stage. What I mean is that I'm not completely understanding yet the behavior of these contact number questions, the maximum contact number question with respect to lattices. Okay, so I'm not yet there on the level of your question, but I'm, you know, moving towards that direction. I'm trying to working on right now is understanding contact numbers with respect to lattice packings. And that is, you know, if I may, I could roll back my slides here and somehow illustrate that a little bit in the three-dimensional case when we have the face-centered cubic lattice, for example. Mm-hmm. You know, that is a special lattice. We love it very much because it exhibits a lot of nice properties. And although I have not stated it here, in this theorem, you know, in this part here, you see that the number of attaching pairs in an arbitrary lattice packing is upper bounded by this number, I stated it. But actually what is proved here more, behind the scenes, the real statement is that if we take an arbitrary lattice packing of n unit boards, then the contact number of that is upper bounded by the maximum contact number of packings of n unit boards centered at some points, lattice points of the face-centered cubic lattice. In other words, the face-centered cubic lattice turns out to be extremal. And I'm trying to, you know, to extend this thing to other lattices, in particularly dimension 4, D4 I'm looking at in dimension 8, you know, the root lattice, 8-dimensional root lattice is a great candidate, and of course in dimension 24, the Leech lattice. So in brief, I'm trying to move towards your direction, but I'm not yet there.
Yeah, but okay, just maybe a question. Actually, look at the theorem, right? And you have a lattice packing and you have a general packing, but still you have, we are talking about only constant. Maybe for this periodic packing it will be similar, right? There's constant, they are just constant a little bit between these two numbers. Can you prove this theorem that there exists a constant such that?
No, not yet. I don't think so, but I agree with you. It should hold.